Let's look at Chiefmate's Stability Examination, July 2019, question number 1. It says a vessel floating in a saltwater port is initially heeled 4.2 degrees to port and has the following particulars: displacement 6207 tons, kg 11.15 meters. Tanks are then ballasted or loaded as follows: number 1 dB tank across ballasted full, number 2 dB tank center ballasted full, number 3 dB tank center 150 tons of heavy fuel oil, relative density 0.84. Freshwater after tank filled. Assume that the above tanks were initially empty and use kg of tanks for loading purposes. On completion of the above, there remains 130 tons of cargo to be loaded. 2 stowage spaces are available, each 5.20 meters port and starboard of the ship's centerline. Using the stability data booklet, calculate each of the following: A. The angle of heel on completion of ballasting and bunkering. B. The weight of cargo to load on each side so that the ship completes loading upright. We will first calculate the km of the vessel, which is at the initial displacement of 6207 tons. The km has been obtained from the hydrostatic data, which is 11.400 meters. The kg of the vessel at 6207 tons was given as 11.15 meters, which was given in the question. We will then calculate gm at 6207 tons, which is 0.250 meters. So when we subtract kg from the km, we will get gm. The next step is to determine the initial GGH. For this, we'll use the formula tan list is equals to GGH initial divided by GM. So tan of list is 4.2 degrees. GGH initial is what we are supposed to find out. And GM is 0.250 meters. So this value has been obtained from here. We have calculated initial GGH as 0.0184 meters. The direction of GGH is port because in question it was given that vessel has been listed to port. That's why we have this value as port. We'll now make the GGH table, which has the following columns: description, weight in tons, distance of centerline, moments of centerline in port, moments of centerline in starboard. So we'll make our first entry, which is the initial. The weight of the vessel was 6207 tons. The distance of centerline was 0.0184 meters, which was obtained from this part. We'll then calculate its associated moments. Since the vessel was listed to port, there was moments only on the port side. There was no moments on the starboard side, so we have written dash. Moments on port side has been obtained by multiplying the weight times the GGH. We'll then make the entry for number 1 dB tank. So number 1 dB tank, the volume of the tank was 255 meter cube, which is given in the ship's particular. And since we are taking in ballast and vessel is in salt water, so we'll be taking in ballast, which is of relative density 1.025. So the volume is 255 meter cube and the density of water what we are filling in the tank is 1.025. So when we product these two numbers, we'll get the displacement. So the distance of center line is 0. This has been obtained from the ship's particular. So since the distance is 0, there are no port and starboard moments. Number 2 dB tank is then filled up, which has a volume of 271 meter cube. Again, since the vessel is floating in salt water, so we will be taking in ballast and ballast would be of the same density as the vessel is floating in. So vessel was floating in 1.025, so ballast would be of density 1.025. So it is again the volume of the tank multiplied by the density, which will give us the weight of ballast. Since the distance of center line is also 0, there is no port and starboard movements. Again, the distance of center line was taken from the ship's particular. Number 3 DB tank, we are supposed to load 150 tons of fuel oil. There is no distance of center line and it is 0, so we have put again dash, so there are no port and starboard movements. Again, distance of center line has been obtained from ship's particular. The last what we take in is the fresh water after tank. So we load 44 tons of water and fill the tank completely. Since the distance of center line is again 0, this value was obtained from the ship particulars. There are no port and starboard movements. So total starboard movements, which is 0, becomes 0 as total starboard movements, and the total port moments is 114.2. The total weight, which is the sum of all these values, is 6940.2 tons. Since there are no starboard moments, so the effective moments taking place on board the ship will be just this value. So we'll calculate final GGH. So final GGH is equals to sum of all the moments divided by sum of all the displacement. So sum of all the moment is 114.2, which has come from here, divided by the sum of all the displacement, which has come from here, which has given us the final answer of 0.0165 meters, and the direction is port. MCQ recommends to take the value of GGH, which is this value or this value, to 4 places of decimal. However, it is still a recommendation and 3 places of decimal are also acceptable. After this step, we'll make a kg table. So kg table consists of following columns, which is description, weight in tons, kg in meters, vertical moments in tons meter. We'll make the initial entry, which is weight is equals to 6207 tons, kg is 11.15 meters. So vertical moments has been obtained as 69208.1, which is by multiplying these two numbers. The second entry is the number 1 DB tank, which is the volume is 255, which has been obtained from ship particulars. And since we were filling in the salt water, as the vessel was floating in salt water, we have multiplied it with the density. So together, they gave us the mass of water inside it. The kg of the tank is 0.61 meters, which has been derived from ship particulars. So the total vertical movements have been obtained by multiplying these two numbers. The number 2 DB tank, the total mass filled is 271 multiplied by 1.025, because this is the volume of the tank and this is the density of water what we are filling in. The kg of the tank is 0.59 meters, and this has been also obtained from ship particulars, which has given us a total vertical movements of 163.9, and this has been obtained by multiplying these two numbers together. Next entry is for number 3 DB tank. So we have filled 150 tons of fuel oil. The kg of the tank is 0.60 meters. It has been obtained from ship's particular. So total vertical moments is 90, which we get by multiplying these two numbers. Since this tank was initially empty and the tank volume is 271 meter cube, which means that the tank is partially full because it has just filled in 150 tons. So there has to be the free surface moment induced in this tank. So we'll make the next entry for the free surface moment, which is FSM. So there is nothing to do with the weight, there is nothing to do with the kg. We'll finally get the free surface moment added in the vertical moments column. So the free surface moment associated with this tank with respect to fresh water was 1142, and this value we have got from ship's particular. Since we are not filling this tank with fresh water, we will multiply it with the density of the liquid inside the tank. So density of the liquid inside the tank is 0.84, which was given in the question. So this is the corrected free surface moment. After this, the freshwater after tank was filled up. So it is 44 tons and the kg is 7.38 meters. So we have got its associated vertical moments by multiplying these two numbers. We'll now sum up the table. So the total weight is the sum of all these values, which has been come up as 6940.2 tons. And we'll sum up all this value and the final vertical moment has come up as 70905.4. We'll now calculate the final kg of the vessel. So final kg is sum of all the vertical moments divided by sum of displacement. So sum of all the vertical moment is 70905.4, which we have got from here. And sum of all the displacement is 6940.2, which we have got from here, which has given us the final answer as 10.217 meters. Now we will calculate the new km of the vessel. Since the displacement of the vessel has changed, the km of the vessel also needs to be changed. So the km at 6940.2 tons, we have got it as 10.670 meters, and it has been obtained from the hydrostatic data by doing interpolation. The kg at 6940.2 tons was 10.217 meters, which has come from here. And the gm of the vessel at 6940.2 tons is 0.453 meters, which we have got by subtracting the kg value from the km value. Now we know our final gm, and previously we had calculated the final GGH. So we can calculate the list. For calculating the list, we'll use the formula tan list final is equals to GGH final divided by GM final. So tan list final is equals to 0.0165, which is the GGH final value, which has been obtained from here, and divided by GM final, which is 0.453 meters, which has been obtained from here, which has given us tan list final is equals to 0.03642. So list final is equals to tan inverse of 0.03642, and list final is equals to 2.1 degrees, and direction is port. The direction is port because if we look at the GGH table, which is here, this table. So the final GGH, we had the direction as port. Since the final lever had the direction as port, so this is because of the same reason that the list of the vessel will also be in port, which is the case here. This is the answer for part A of the question. The part B of the question asks us to calculate the weight of cargo to load on each side so that the ship completes loading upright. For calculating this, we'll make another GGH table, which has the following columns, which is description, weight in tons, distance of center line in meters, moments of center lines in tons meter in port direction, and moments of center line in starboard direction, also having a unit of tons meter. We'll make the first entry, which is after ballasting. So after ballasting, the weight was 6940.2 tons, and distance of center line was 0.0165 meters. So this is the value which we had obtained earlier as the GGH. If we look before, this is the same value which we had obtained when we were solving the above table. When we come back to our table again, we obtain our moments of center line. So this is obtained by multiplying these two numbers together, which will give us the answer of 114.5. Since the GGH was in port direction, so moments has to be in the port direction. So that's why the starboard has dash sign, which is nil. We'll now assume that cargo to load in port direction will be x. So the distance of central line where the cargo is supposed to be loaded is 5.2 meters, which was given in the question. Since we are assuming that cargo is to be loaded in port direction, so the moments associated with it will also be in the port direction, which is this. And we know that moments is obtained by multiplying weight times the distance of central line. In this case, it is x times 5.2, which has given us 5.2x. And starboard side is again nil. Now, cargo to load on starboard side would be 130 minus x, because total cargo to load was 130 tons. And if we consider that we have loaded x tons of cargo in port direction, then the remaining cargo to load in the starboard direction would be 130 minus x. The distance of central line is 5.2 meters. Again, this was given in the question. And its associated moments would be 130 minus x multiplied by 5.2, which will give us the answer of 676 minus 5.2x. And since this cargo was loaded on the starboard side, so the moments associated to it are on the starboard side, and on port side we have nil. So the total weight of the vessel is now sum of all this value, which is 6940.2 plus x plus 130 minus x. So the x and minus x gets cancelled out, and we have got the numerical value as 70.2 tons. The sum of all the port moments is 114.5 plus 5.2x. Since 114.5 is a numerical number and 5.2 is an algebraic expression, so we need to keep them separated. That's what we have done here. We have done 114.5 plus 5.2x. We have kept both the numerical value and the algebraic values separate. The same thing has to be applied on the starboard side. So starboard side, we have total moments as 676 minus 5.2x. So we have kept the numerical values and the algebraic values separate. Now, in order for the vessel to be upright, it's very much important that the effective listing moments for list is equals to 0. So effective moments is nothing but difference between port and starboard listing moments. Once the difference between port listing moments and starboard listing moments is 0, at that time the vessel would be upright. In other case, we can also say that port moments is equals to starboard moments. In this case, the vessel will be upright. So the port moments was 114.5 plus 5.2x, which we had got from here, and starboard listing moment is 676 minus 5.2x, which is from here. When we solve further and took all the algebraic values on the left hand side of the equation, and we took all the numerical values on the right hand side of the equation, which we got as 10.4x is equals to 561.5, and x we have got it as 54 tons. So weight to load on port side is equals to 54 tons, because we have assumed x to be the cargo loaded in port side. So here we have got the value of x, which is the cargo loaded on port side, which is 54 tons. Now cargo loaded on starboard side was 130 minus x, which will give us 130 minus 54, which is equals to 76 tons. So weight to load on port side is 54 tons and weight to load on starboard side is 76 tons. This is the answer to part B of the question.